So, I would say welcome everybody to this stream by the Perfect Target. And what do we have for today? Well, as you can see from the card, we're continuing with our endeavor to write a compressor that is similar to the LZSS, so sliding window compressor. And so far, we have already done quite a number of things. So we finished the library part of the encoder and the compressor. And yesterday we finished with a mock decoder, so that our first task in hand is to write the decompressor. Without further ado, let's go and write that. All right, so as you can see from the example that we created about the encoder-decoder, what would be the task of a decompressor? The decompressor basically would run a loop like this one, right? It would create a decoder, but of course, instead of receiving the result, it will need to receive a way to read from files. And that's a mistake that I think we did yesterday. When we wrote the mock decoder. No, not for the mock decoder. For the mock decoder, we made it so it was reading from a stream, which again for a mock is not a problem. For the real decoder, of course, it has to be configured with a reader. Same with that for the real encoder, we did it with a writer. So let me show you the encoder for a second. So the real encoder. So it had a writer, so an object that implements the write trait. So obviously for the decoder, we're going to do the complete opposite. We're going to have a reader, which is an implementer of the read trait, and then a new that is configured the same way as the encoder, even though, once again, we just need one parameter for the decoder. Well, no, we are going to need both. We just need two parameters. We are going to be able to configure the famous functions. For the decoder, we saw that we only need public access to one of the functions, get max length literal, which is renamed for a decoder to get output buffer size, which allows the decompressor to have a buffer of that size. So in case the decoder reads a literal block, it can directly put the literal in that buffer, avoiding double copy of the data in that literal block from the input to an internal buffer, then to the output buffer. So that's an optimization that we did yesterday. So yes, our decompressor will need to create a decoder, or it will be receiving a decoder, sorry, and then it will enter a loop in which there are two ways to exit that loop, right? Depending on whether or not end of file symbols are configured, right? If end of file configured, then the loop finishes when end of file is red. What do we do when that is not the case, when this is configured to be false? Then I think the easy way to do it would be to make the decompress function to read for a certain amount of bytes, right? Because if we don't have end of file, we assume that we get another way to receive the length of the original file. So that's a parameter. And to handle the case in which we do have end of file, that parameter has to be an option. Then inside that loop, once again, is going to receive a symbol and then process the symbol. Process the symbol, however, is going to be more complex, right? Obviously, for end of file, there is little else to do. For references, it needs to go and copy that reference, which is not hard to do. And for the literal, it has, the decoder has already copied the data. So the goal is to move to slide the output buffer for the next symbol. That's basically what we need to do. That being said, we need to consider a couple of things. If we take a look at the compressor, the compressor, basically how it works is that it has, it receives an encoder, and then let me show you. And it has an internal buffer. So the user can put data in that buffer, and then using the method compress and flash, that data gets compressed from the buffer to the encoder. So how it is going to work for the decoder? For the decoder, the decompressor is going to ask the decoder for symbols and put them where? So the data needs to be put into a buffer always for LZSS, because that buffer becomes the window that is needed to decode future references to that part of the window. So there is no way we can write directly to a file. So in the spirit of having a linear buffer compression algorithm, as we have here, we're going to do the same with the decompressor, and that the decompressor that we're going to write also has a vector as a buffer, and it's just going to put everything in the buffer, and that's it. So if we later want to send the data to a file, then we will do so just by taking the buffer and putting it on disk. Let's take a look at the example that we made for the compressor. The compressor did something similar. It first read from beginning to the end the standard input to a buffer that it was compressed. So for the compressor, it would be basically we would create an encoder coming from, we don't know, that depends on the implementation of the encoder. The first decoder that we're going to have is the mock decoder, of course. that acts as the input, and the compressor then sends the data to a buffer, then again with something like get buffer, because for the output this need to be read-only. We can just send without write all to standard out. That's my basic idea. So let's work with that. So I'm going to copy the compressor. Compressor, we don't need all this blurb again. We need the decoder. So yes, the decompressor, as I was saying, is going to own its output buffer, because as I have already mentioned, we need to, in order to use it as the window anyways, but we just need to have a public read-only view to it, while the input is left to the code increment. And we will talk about extending the size of the buffer, but that's on internal here. All right, so we're going to do a parallel. The compressor that receives a mutable reference to an object that implements the code. The buffer is going to be different, so I'm not worried about it or the comments. We need that now, and that's something that it doesn't look apparent at the moment, but I will show you why that's the, I mean, that's the case. In theory, we can work without a now, but for the moment, we're going to have a now, and we'll see later if we can refactor the code to use other things. I think that now is still very useful, but I think that thanks to the length of the buffer and potentially other parameters that we already have available, we won't be needing a now. But once again, at the moment, let's try to write it in a simpler way. So I just put it out, a typo in the compressor. Here. So let's come back. And this decompressor, we call the decoder for information regarding compressor's efficiency, maximum reference and distance, and for decoding the input symbols, little blocks of references. Perfect. So we have decoder, So we just need the decoder, an empty buffer, and now. All right. So the advantage of the decompressor, as we already saw in the example that we did yesterday, is that it is very simple chip. Basically, we said that we would have an option for original size, so we can decompress files when the need COF is not configured, right? In fact, let's take a look at that. We're going to add debug assert, in which self decoder, if I need EOF, then I can still have an original size. It's a bad idea, but you know, why not? That's valid. But if we don't have an it's a web, then the original size has to be something. I cannot be left to nothing, because then it doesn't know when to end. And at the moment, with the coders that we have, either the mock one or the fixed size align to byte, the coder, later the coder, that is going to be a problem. But it will be when we have a more advanced decoders. Why do we have a message here? Okay, who knows? Anyway, so how does the decompressor work? So we already have a decoder, right? That comes as part of the compressor object. Basically, what we need to implement is roughly this. So the first thing that you may think is, okay, we don't need an output buffer because we actually have a buffer. That is absolutely correct. But here's the thing. This buffer needs to be extended beyond the window, beyond what we have compressed so far, in case the next symbol is a literal. So the decoder has written into that part of the buffer. Okay, that part of the buffer, I'm going to call it the read ahead. Which is actually a write ahead, so that the decoder can write into that write ahead. So we always need to make sure that we have enough space there. How are we going to do that? So let me a second, I'm going to take inspiration from the other implementation that we did. Yeah. So what we're going to do is write code correctly. We're not going to bother with this directly, but we're going to have a function to do that, right? So first we're going to extend the buffer, or extend for the write ahead buffer. And for how much needs to be extended. So obviously at the beginning needs to be extended for the size of the buffer, right? But let's imagine that we receive a literal, and that literal block only has 3 bytes. Then we only need to, next time, for the next simple, we only need to extend the buffer for 3 bytes. So firstly, that means that we need to call this not in the initialization, but inside the loop. And instead, what we need is a variable. And I'm going to call it lines. Right. Okay, I know it's a mouthful, but I think it tells us what we need. Those are the bytes in this form right ahead. That is going to be this, the maximum length literal. However, we don't have access to it directly. Instead, we're just going to call the decoder to give us the output buffer size. Right, so with that, we solve this. And basically, yes, what happens is that in case we have a literal, go to the literal tells us what is how many bytes have been used from this write ahead buffer. So obviously what we're going to do is subtract those. So next time we go into the loop, now serve this extend write ahead buffer will be extended by the many bytes that are needed. Is that how it works? No. Wrong logic for me. So let's think again. If this is the number of bytes, as soon as we call extend write, we don't need any more. Then we will need more if we have a literal. So this solves the logic here. All right, so symbol is unknown. That's correct. Why? I think it's because of the comment. This doesn't make any sense. No, okay. No worries then. Okay, so we can do again small optimization. Is having the if about the extend here and not inside the function. Okay, so now we have the logic about the write ahead. Then we will need to do other things, right? So if the symbol, and yes, of course, now the write ahead buffer is equal to what? Is equal to our buffer, our vector, right? But we have extended it from now until the end. That tells me another thing, is that here, when we have a reference, we also need to extend the buffer. Right? Because what has happened is that we have pushed we have sleep, then now to the right anyway. So as you can see, this the reason why I don't think we need is we may not need now is the fact that now is always tied to a combination of the amount of bytes that we need for write ahead and the length of the vector. Right? Basically, now most of the time it has to be equal to size of the vector minus the size of the output buffer. When things go fine, here it won't, it will be end of the vector minus this plus this. No. That would be something to do another time. So I think that is that's the write ahead buffer. So then we're going to call our decoder, next symbol, and then the write ahead buffer. Then if it's an end of file, we finish, and then is it okay? Do we need to return an okay in that case? I think so, because remember that if the decoder is configured not to have end of file symbols, but it decodes an end of file, it already provides an error. It will end with an error. The only way we reach this is if there is an end of file and it is the correct place. Now, I don't think we should return just this. We should return the vector correctly, and that is not what happens here. When we finish, we need to adjust the buffer. So basically it's just the buffer size is just from 0 to now. We remove the write ahead buffer, and then yes, we can return an OK. Because the user can figure out how many bytes were decompressed by just looking at the length of the output buffer. So yes, that part is okay. So now what else do we need? So for the OF, we don't need anything else. And yes, we could write this here instead of having the break, but just in case. I don't like to have forever loops, or quote unquote forever loops that end only with a return. Call me superstitious. I prefer it this way. The next thing will be for references. Obviously, for a reference, when we get a reference, what we need to do is to copy reference. Okay, and for the literal, the decoder has already written those bytes into the write ahead, so there is nothing else that we need to do. I don't like the fact that this is the same, but what I can do is, no, I cannot have a let because then I have a break. Okay, I will think about that, how to refactor this code later. So this basically completes the decompressor. We don't need to compare prefixes, find matches, flash pending literals, accumulate literals, compressing the files. We don't need to do any flushing. We must, however, implement the get buffer. But because this is actually not mutable, I think we should return just the buffer as a slash. So obtain a reference to the compressor. This the compressor owns its output buffers acting as it actually acts as a context window, but the user needs to access it in order to work with the sign up. All right, so here color config order, and we're going to need some tests, but we'll think about tests later. At the moment, this is the decoder, so we need to write it. We just need 3 functions. The first one is the extend write ahead buffer. that receives a no, so we actually don't need this 0 here. Now that I think of it, because it's always changed. So, oh, this is parts unit size and probably to add and assert that the bytes needed is 0 just in case. So how do we extend the buffer? The easiest way to do that is to get the buffer and to do an extend from slice. All right, so extend from a slice, it receives an slice, for example, of zeros, and how many, right? So we have a slice that is 0, and the length is bytes needed, and that will be all. What's the problem? We don't have this slice. Worse than that, we would need to create that slice over and over and over again, basically for every symbol. Instead of that, we're going to create it one time. And why do we have this? Turn this variable request the color is border. Yeah, okay. Yeah. Let right now and equals so this, and now that is captured. Yeah, soft. And that means that now we can do this chicken brick, and we have the extended function. No, what does it say that this method takes an argument but to supply? Oh, yes, you're right. Okay, cool. So one done, two to go. No, two, there's only one. Copy reference, right? It's the only other function that we're missing. And now you will see how easy it is to implement this given the previous function. We're going to debug assert. No, we don't need to. We need to debug assert here. We actually just need to do a serve buffer extend from a slice. I mean, it is from within. Assert C must be arranged that comes. Yes, no, we cannot do that. Sorry. And so the problem with extend from a slice and extend from within is that they are not going to work because they don't work if So we have two cases, right? We have one case in which the distance is more than the length, because in that case, all the bytes that we are reading or that we're copying are already in the window. So if that's the case, we can actually do an exit from within. The other case is when distance is smaller or equal to the length. You need to double check the logic about the equal. Yes, I did it. Because that means, let's say we go to a distance of 1, so we're going to copy from the previous byte to now, and we're copying 5 characters. So characters, right? Something that happens like with round length encoding, etc. That's a trick that LMPLC allows, is to have references that go beyond the quote unquote the future. In this case, however, because it goes into the future, basically the range that we're copied from is built dynamically as we copy data. We cannot use extend from within. So that's what we're going to do. So this needs to be passed along range bounds. So for example, here is says 2 dot dot of this one. So 0, 1, 2. So it's going to copy CDE, correct. So the range is between self now minus distance to self now minus distance plus length. Once again, because in this case, distance is larger than length, this minus this minus this is strictly smaller than now, as it should be, because now doesn't exist yet. And by the way, this is why this is okay. Yes, no, right. So with that, we have that solved for that branch, and I think it is valuable because probably this method has been optimized for years. And now in this other branch, once again, we need to do things by hand, copy byte by byte, because we don't have any other option because we're building things as they come. So basically for byte in. For index in 0, so length self buffer, and we're going to push self buffer of now minus distance plus index. Why? Because here, even if distance is equal to length, so this 0 buffer now is copied. Yeah, I think this logic is wrong. I mean, it is not, because the way distances and lengths are constructed, I think. But we will see. I'm not sure about this. Oh yes, we needed another function. I knew that there were three. Adjust buffer. Okay, this is basically we have finished the comparison, but we had some data in the write ahead buffer. So we're going to truncate to now. And that's it. So we lose the write ahead, and now the what I was going to say. The buffer has the right size. Now, this doesn't take into consideration original size at all. In this buffer, we're just exiting, yeah, because we have the end of file. I always forget how to write an if let. Oh, it was correct. Cool, cool, cool. I'm learning some Rust, guys. Ah, so what's happened here? Oh, it's the other way around. Some size. Right. So what's the other issue here? What do you mean? Okay, so let's remove this function that we're probably using here anyway. Okay, that works. Okay. So now this builds. So I'm thinking about distances equal to length. Can that happen? I don't think it can happen in any way, shape, or form. But in any case, we still have, so this is when distances are smaller than length. Okay, yes, that's I see that's a problem. That's I see. So save now. We reduce the distance, but the first index is 0. So because distance is never 0, and we don't know that for sure here, for the mock decoder, we are assuming that. For the read decoder, we must make sure that doesn't happen, that distances are 0. And I think that's trivial, the way the decoder works. Distance is not going to be 0, it has to be at least 1. So this looks at the window initially, and then it picks on. Okay. So I think this works. So let's add some tests, shall we? So the first thing that we're going to do is to test the extent where the head buffer. So first of all, we need to create a decompressor. And the decompressor needs a decoder. So that's why we have implemented this, I guess. First, we are going to need a constant for the configuration. Okay, then we're going to create a folder. The decoder needs the input buffer. That's true. But it needs the symbols here, not the symbols from the decoder. So we create this buffer. And then we create a decoder with a reference to the buffer. And then we need to pass along if we need end of file and the configuration. And now for the decompressor, the new method needs just the decoder. And this, yes, this doesn't need to be mutable because we're not doing nothing yet. So this is about calling the extend right ahead. So before that, we're going to do an assert equal that in the size of the buffer excuse me, that the size of the buffer so we are going to assert that the buffer is empty. Once again, compressor buffer is empty. Okay, that's the beginning. Then we're going to extend it by whatever we want. We have a debug assert for 0, but I think that's not going to happen. We have it there as a safeguard. So maximum literal, just the maximum, and we need to make sure that the zeros a vector is created accordingly, and then we assert that actually we have that many bytes in the buffer. Okay, everything passed. So this is the easy test. In order to have another test, we could, for example, manually decode a literal block. Or we can do that by hand, just by manipulating the now. Let's say 3, right? This would be like if we had decoded a literal block with 3 zeros. It would be equivalent to that. So we're going to extend the buffer by 3, right? Which is what happens here. Bytes needed 3, serve now plus 3. So then we extend 3. And once again, we're going to check that the buffer is the maximum size. And it failed. Oh yes, it failed. Because we're taking a look at the length and obviously the length is increased. All right, so that's basically how the write-ahead buffer works. And I had a little alarm that tells me that it is time to take our stretch break. So let's do that. Give me 1 second, I'm going to put some music. There. So stretch, hydrate, especially so if you are living in a place where the weather is hot, like me. And I will see you all in 2 minutes. And we're back. So let's continue with the tests. We have tested the write-ahead buffer. So we extend the write-ahead buffer. I'm not going to test adjust buffer because I think it's self-evident that what it does, that it works. I mean, this comment is not useful at all. So what about copy reference? Yeah, I think that we can have that. That being said, I think that copy reference is wrong. Let me tell you why. Here I'm using extend from within, right? But because the buffer is waiting for a literal block, the buffer is not pointing at now, it is pointing to the end of the to the end of the buffer, of the write ahead buffer, right? And moreover, this is going to copy, yes, this is going to copy L characters. So how can we do this? One thing that we can do, it will be to adjust the buffer and then extend from within. Now, this works because the vector can keep the memory that was allocated from for the extension if you need it. So this actually is kind of cheap. Now, the disadvantage of this is that then when a copy reference returns from this branch, the amount of data in the read ahead buffer is 0. While if it returns from here, this is also wrong because we are pushing at the end. So that's a good thing, because that means that in either case, if we do the truncate, the end result is that we need a full read ahead buffer if we do the adjust buffer at the beginning. Problem being, what I was thinking instead is instead of using a push in this branch, taking advantage of the fact that the memory has already been allocated, and just copy, right? So self buffer of set plus now plus index equals, so let me write it. And while I do think that this is actually faster, because we don't need to call push, and push doesn't need to know if there is enough space of node. We know there is enough space because it was pre-allocated. The issue now is that the function returns from this branch with a need to extend the buffer for length, but when it comes from here, if we adjust the buffer and we extend from within, it basically needs everything, right? We have lost the extended buffer. Or we could do a copy within instead of an extend within. This copy service from one part of the slice to another part of the service using a main move. Two ranges may overlap. That is good. But as you can see, the ends of the two ranges might be less than or equal to the length of the buffer. But that happens even here because of the extension. So I'm just being really, really silly. Probably am. And all of this is just buffer copy within and here it says 1.5. Eight. Zero, 1, 2, 3, 4, 5, 6, 7, 8. Yes. Okay. So it's just giving the start point because the end point is obvious. Because the length needs to be the same. That's correct. That's correct. So we will need just to copy the reference as a serve buffer from serve now minus distance. No, it's just a range. RG is just a range. So from here to here, and this needs to be copied to here. This is okay. Just give me a second thinking. Let's test this. So first of all, as always, we're going to need this to have the compressor, so we can call copy reference. And now we're going to do some tricks. So the first is we're going to to push an A into the buffer. There is an error somewhere. Here. Yes, it's self-state. Compressor buffer push. All right, so the buffer has right now a length of 1 and no write ahead. So if we try now to do a copy reference, that is going to fail like tremendously. So the first thing that we need to do is to extend the buffer to its maximum length for the write ahead. And now in theory, whatever reference we copy, it should fit. Except that it doesn't. And I'm going to show an example where it breaks. So we need to think about that. So first we're going to do a test where it works. And the reference fits in the window, meaning that we need to call And where do I have the other file? Oh no, I have it in another branch. That is on local, so I cannot switch. Sheesh. Okay. So let's write everything. Memory. Reference lengths. From here to here. The here to here are the encoder gate break-even length. So in it get max reference. Bits for distances. And the literal lengths. Okay, so here we're using the real encoder, right? The fixed byte coder. We don't do anything with the output. Yes, this is the standard output. Okay, so there we go. Okay, so if I do things correctly, then it worked first time. Now, so as you can see, this is the issue. The buffer that we're creating is long enough for literal length, right? But it's not enough for maximum length of references when we're doing a real example, right? And let's imagine that we plug in those numbers here. So break-even length is 3, maximum reference is 130, the distance is 556, and is 127. Now, because of this, it happens, or it can happen, that I can copy a reference, sorry, I can copy a reference with distance. So copy references in length distance with a length of max length reference, which is correct, and a distance of 1. Okay, this is valid. This is a very valid example, something that is going to fail the test because the ranges are wrong by exactly the 3, that is this minus this. Okay, so that's a lesson. So how can we find out here So here, if our buffer has enough read ahead. So the read ahead is actually insert buffer length minus self now, right? And this is the amount of read ahead that we have. If this is more than this, we need to increase that. But that still creates a problem. Is as you can see now, it says that the byte needed for read ahead is L, which is not, because this is more than what we need for here. So this block is wrong. What we need instead is use the other thing that I was talking about, which is instead of copy within, we use an extend from within. By first adjusting the buffer size. Okay, by doing this, this is going to work every single time. But we need to change the logic here. Here, bytes needed for read ahead is like at the beginning, because we don't have any any remaining read ahead. Cool, 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 cool. Yes, I like this more. Especially because now in theory, oh, come on. Oh, now we have a different problem, a different error. That's much better. So now the error is in 114 here. In the extend right buffer in 1.4. Why is that? Yes, because once again, I'm using the wrong variable. Yeah, and now we have the problem that is the reason why I was not using the extend, which is because it doesn't work. No. Yeah, because it doesn't work in this scenario with a length of 131 and the slice is too short. So would copy from within actually work? Oops. it fails for the same reason as before, because the end index is above that. And another thing that it won't check is memmove. So copy from within. So copy within is not going to work because the information says that it copies the data using memmove. A memmove copies the bytes from the memory area SRC, like if it was moved to a temporary array, and then the temporary array is moved to destination. So that doesn't work for the logic of the overlapping that we want to apply. So that's not going to work at all. So I think that we need to go back to the drawing board. And let's think about again with the two branches. Because yes, when the length is smaller than the distance, then yes, everything they want to copy can be copied within. The issue here, so this could work, except for the fact that the part of the destination can be short. So how do we do that? Because basically what we're saying here is that if the length is smaller than the amount of data that we have in the write ahead buffer, we need to extend the write ahead buffer to length. And then of course, we don't have any write ahead. However, if this length is smaller than the write ahead, this works. The problem is we have remaining write ahead. So what if I return argue size, which are the bytes remaining in the write ahead buffer? Because then if if length is less or equal, let's calculate the write ahead. If the length is less or equal than the write ahead, then we're going to have remaining. The remaining is actually with ahead minus left. But if not, we have two issues. First is that there's no remaining, but we may need to extend. And we need to extend by red ahead, sorry, by length minus red ahead. Okay, that way we have extended that amount. And then we call now we can copy from within, because we in every case we have enough amount, and we return remaining. So that solves the problem on the branch. But now that means that when we copy a reference, the bytes needed for write ahead is the maximum minus min. Cool, and that solves the issue at hand. So now what about the other branch? The other branch is when the distance goes above the length. And in this case, we could still in theory copy up to distance minus 1, substituting it here, and it would work. But then we will need to copy the remaining again. So I don't think it makes sense to complicate this a lot. Instead, we're going to go for the kind of brute force of adjusting the buffer and having the loop that we had before. With the pushes. And in this case, remaining is 0 because we're pushing. Yeah, I think that is much more complicated, but it should work now. It works. All right, so if we think about it, this implementation of copy reference has 3 branches. So when length is less than distance and we have enough read ahead or not, which is not this case, because this case length is equal, not less. So for the first one, the first test, we're doing a copy reference of 1, 1, right? And that means that we're coming to this branch. Does it make sense? No, it doesn't. I think because so we have a 1, right? So the length is 1, is less than the word ahead, so it's okay. And we just we copy within the single byte before you. So now the first test goes to this first branch, in which length is less or equal to distance, and the remaining is going to be read ahead minus length, because the length is 1, read ahead is longer than that, and we copy. So the result of this, which is something new that we need to compare to, is now, because we're coming from this branch 1, remaining is going to be read ahead minus 1. Read ahead minus 1 is 126. Okay, it's going to be config max length literal, which is what the amount which we expanded it, minus 1. These are the remaining. Now, because of that, we actually work with the second example. We need to extend the write ahead buffer by 1, which is 127 minus. Perfect. And now we have this example in which the length is obviously way larger than the distance. So length is larger than the distance. So we adjust the buffer. And then we copy this by hand and return 0. And now the buffer should be equal to ace 2 plus ace. Yes, that's nice. See? Yes, it is. All right, so we have manage two of the branches. So case length small distance length is more than height size. This is the case in which the length is larger than the distance. So let's update this and this, and then the case if the smaller is more than the distance, but the length is larger than the width. Okay, size. And now we can do that because now we can do copy reference with a distance of now. So I want to copy from the beginning, and the length is config max length and reference. So we know that the distance now is longer than the length because the length is this, and now is actually 2 plus that length, right? So the length is smaller than the distance, and the length is larger than the red ahead because the length is this, and the red ahead size is this. So this would be an example of the third case for this function. So we need to figure out what is going to be the remaining, and the remaining is 0, right? Copy reference as 0 when the length is larger than the red height. Yes, 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 yes. And now the last assert, the contents. Is the buffer it should be like that. Constant expression. Okay, so 2 plus 2 times config max reference. You're happy now? Telling me how to do maths. and it works. Beautiful. So now the powerhouse of the compressor, which is keeping the red ahead buffer long enough for the coder to be able to directly copy a little block there. And the copy reference are done. Adjust buffer, once again, it is triggered to write. And decompress, I think it is kind of trivial, right? We we start the write ahead buffer. We initialize the buffer, the amount that we need for the write ahead buffer. We have a first condition to exit the loop. If and we have original size. I want to, no, I was thinking, sorry, I was thinking that this maybe maybe we can change it to a while let, which I think it exists. Let's see if cargo quickly say something like that. Not at the moment. Let's say to collapse. These two ifs, which I didn't know you could do. And if so, that basically answers my question about the while. The while let. This really looks like a while let. Let me show you. I don't use it much, but this doesn't work the way I want, but it can. Because same way that the if let allows us to put some conditions. You see here, with this only just doing an if let, a simple if let. But then the if let can be collapsed with our next if. Maybe we can write this as a while let. Let's try. While no, I see why it cannot be done. Okay, because actually the while condition is the negative. So while origin size is known, or, and now we will need to do the unwrap. or the original size is larger than subnode. Oh, return. Yeah, like this works. I like it more in a sense. Um, so I like it more in the sense that a loop there with an if break that stings to a while. But on the other hand, we have another condition to exist, so it's not a pure while. So using a loop would tell us, hey, maybe there are more ways to finish the loop. But you know, I think this makes for more elegant code. So let's keep it like that. And that means that we have the tests. We're missing the documentation for this one, which is basically a documentation about the meaning of original size. But I think that, yeah, let's compress the input buffer and the input buffer close to the decoder. Compress the decoders buffer. If the decoder is configured to be EOF, original size will be set to none, and the method the n ethnic remain EOF. Otherwise, it will compress the value wrapped with the compress as many out bytes as the value wrapped in English mixers. I think this makes for a basic documentation. So we have documentation here, documentation here, documentation here, documentation here. We have the tests. So I think can do cargo clipping, cargo test, everything pass, cargo doc. And now we have the compressor with the documentation. So I think I want to choose this decoder to a reference. if the coder is configured to need UF. Yeah, I think I like this. Everything seems to work. So, in terms of commits, I think I made a change to compress. I made a change to compress, which was a typo. So I'm going to include it in the commit anyway. Change to librs, of course. Change to the compress example, so it print out the references, etc. This is something that I have in another branch, a testing branch that I'm doing. So I like it. I'm going to keep it because this basically allows me to copy the values into the mock encoder decoder configuration, which is quite useful for actual tests. So I'm going to keep it like that. So yes, please. And the compressor, which is any file. And there we have it. So commit, feature, right. And LZSS like the compressor. Please also exist inside for in compressors. All right, so are we done yet? Not really. So in terms of examples, let me remove some things here. In terms of our examples, at the moment we have 3 examples, right? One is encoder dump, which is dumping the symbols to the output. I like to keep it like that because I will show you later in another stream a use case for this, which is actually how we can optimize the coding that we are now using fixed byte coder, how to optimize that with a variable length bit-based or bit-aligned coder, quote-unquote an entropy encoder. And this can help us to figure out that. That's the first example. The second example is just a compressor. It's just a compressor that just works. It gets one file in the input, one input file, one output file, it works. So the goal would be to create the compressor, right? The thing is that in order for that to work, we first will need to implement the actual decoder, not the mock decoder. So this is actually, I want to say the decompressor that corresponds to this compressor corresponds to this other card, which we're not doing at the moment. And the third example is the encode decode. And this is using the mock encoder to get a real input file, compress it, and then at the moment what we have is to decompress, is manually decompress it and show the symbols. But here's the thing: to show the symbols, we already have the encoder dump. So obviously encode the code would be much more useful if the output was an output file that was the same as the input file, right? So how do we do that? We configure the decoder. And now we configure a decoder, the compressor. That receives the decoder, right? It doesn't need anything else. It's the decoder. So we just call compress. And because we have configured both the encoder and the decoder to use end of file, we are going to decompress until the end of file message. And at the end, what we have is the buffer. So what we're going to do now is to get the IO std out write on of the buffer. And that's it. Basically, now we don't need the symbol. Then we don't need the code. Right. So now we have an encode decode example that basically takes an input file, it creates an output file by compressing and decompressing it, but it is using the mock encoder and the mock decoder to pass the information between the compressor and the decompressor. So it's not a full end-to-end example, but it can be quite interesting, I think. So cargo sample input code, the input being the license, the output is the test output. Boom, it says that it works. And here we have, if I binary compare the license input test output, they should be the same, and they are the same. So congratulations, we have a compressor and a decompressor that they work well with each other. The problem is that at the moment they are talking to each other using mock symbols. The next step is obviously to implement the byte-oriented decoder that matches the byte-oriented encoder that we already have, because that means that the decoder, a byte-oriented decoder, is actually reading from an input file, matching the output file from the byte-oriented encoder, and basically that will we implement our basic compression system from end to end with real compression. So let's add this modification as its own commit. So this is not a feature, this was an improvement. How do they call this type of commits, which are not features, they are not features, not fixes. I don't have a nice name. It should have, it's not a feature or a fix. It's an enhance. Let's see if the actual description of completion of commits. Feature fix. And that's all? Feature fixes? Okay, there can be more. Fix, feature, build core, feature, CI, docs, time refactor, perf test, and others. That's what I want, another. All right, so it's a feature. Then, so feature, example, the code, outputs rest. Okay, so with that, we basically have finished this card. The next step would be, once again, creating this byte-oriented decoder. And I think that's what we're going to do tomorrow. Just because that's the last stream of the week. So if we can push it, we can basically finish the project tomorrow. That will be a nice end of the week for my streams. So yes, I think that's going to be all from me. So thank you once again for joining me to the streams, or if you are watching this as a VOD on either Twitch or YouTube. Thank you for watching. Hello, YouTube. And what this has been the Perfect Argent signing off.